Hello everyone, welcome back to this online class. Today we are going to look at numerical integration, and in particular we are going to look at the Simpson's third rule. So we have this question, we are asked to discuss the Simpson's third rule and hence work out the following questions. Number one, estimate the integral that is from 1 to 1.3 of root x with respect to x using Simpson's third rule with h is equals to 0.05. Find a bound for the truncation error. Number two, how many subdivisions are required in using Simpson's third rule for the estimation of the integral that is from 0 to 1 of exponential negative x dx correct to 4 decimal places? So before we solve those two questions, let me discuss this Simpson's third rule. Of course, you remember that when you talk of numerical integration, our task is to evaluate the integral that is from a to b of f of x dx, which I told you is the same as the area of the region bounded by the x-axis, the graph y is equals to f of x, and the lines x is equals to a and x is equals to b. So that's an area problem. So let me sketch the region. So we'll have something like this. X-axis is this. Our y-axis is this one. So let's say we have this kind of a graph. A graph of y is equals to f of x. Something like this. So that here is where we have a, and somewhere here is where we have b. So this region enclosed by those two lines, x is a and x is b, and the x-axis and the graph y is equals to f of x. That's what we mean by the integral from a to b of f of x dx. So it is the integral. It is this. Now, what do we do? There are two steps for you to be able to come up with the Simpson's third rule. The first thing you need to do to be able to estimate that region, of course, this is only valid. There's a note that you need to take note of, that f of x must be continuous in the interval AB. F of x must be continuous in the interval a less or equal to x less or equal to b. It must be continuous for you to be able to use this rule. Or even in the trapezoidal rule, we require that f of x must be continuous in that interval. Now, these are the steps. The first thing you are going to do, let me use another color. Step one, in step one, you're going to divide the interval AB, divide the interval AB into n even subintervals into n even subintervals. This is what I mean. So we are going to subdivide so that we have, let's say here, let's Now, A is the same as X naught. Take note of that. And B is the same as Xn. So when you subdivide here, we'll have X1. Bring another one. That is X2. Continue. X3. Proceed to X4. There are so many of them in between. And then the last 3 is this one. This is Xn minus 1. And this other one is Xn minus 2. So those subdivisions are from X naught all the way up to Xn. So these are the intervals. We'll have X naught, X1, the first interval, followed by X1, X2, and the second interval, etc. up to Xn minus 1 up to Xn, the last interval, each of width h. They have the same width. So that is h in this case, h, h, h. So you can write here that each of width h. And you know, we said h is the same as b minus a over n. This h is equals to b minus a over n. So that's the first step. Now the next step, we write step 2. What you need to do in this step is to fit Newton's forward difference interpolating polynomial of degree 2, forward difference interpolating polynomial of degree 2. On each of the n over 2 subintervals, on each of the n over 2 subintervals. This is what I mean in general is written as xi to xi plus 2. Of course, I is equals to, we write for I is equals to 0. Now instead of 1, you go to 2 for all the way up to n minus 2. Why are we picking that? Let me explain. So look at, we are picking any two. Remember in the trapezoidal, you are picking just each strip at a time. But when it comes to Simpson's, a third rule, we are going to pick any 3 points at a time. So point A, point B, point C. When you have 3 points in a table, 3 data points, it means your polynomial must be of degree at most 2. And so that's why we talk of Newton forward difference interpolating polynomial of degree 2. So that I pick these 2 strips, these are 2 strips at a time, and that's why you see we are having xi to xi plus 2. So when I is 0, that means I'll be taking from x naught all the way up to x2. 3 points at a time. Again, so that means that will be the first area. So this we call it area 1. So between any 3 points, you can get a polynomial, interpolating polynomial of degree at most 2. Again, you pick point C, point D, and point E. Again, 3 consecutive points at a time, fit a polynomial of degree 2, because 3 data points will give you a polynomial of degree 2. So that means I'll have these other 2 strips considered together at the same time. So that will take us from x2 up to x4. And so that's explain why I is equals to 0, 2, 4 in that order. etc. Even these other ones, you are going to treat them at once, the last 2. So having explained that, Let me write here the reason. The reason is that since we can obtain only second order differences, since we can obtain only second order differences from any three consecutive points. Any three consecutive points. So let us recall the Newton forward difference interpolating polynomial of degree 2. So we are going to say that therefore where we have f of x, we are going to approximate this by fi plus s forward difference of fi plus s minus 1 over 2 factorial times the second order forward difference of fi. That's our interpolating polynomial of degree 2. Now, the area enclosed by the curve y is equals to f of x, the x-axis, and the lines x is equals to a and x is equals to b is now given by, remember now here this is area 1, here we'll talk of area 2 all the way up to the last one, which is area, we can talk of area n. So that area is now given by, so you can say that therefore the integral from a to b of f of x dx is equals to, we are integrating from x naught to x2 of f of x dx, plus the other one is integrate from x2 to x4 of f of x dx. I continue all the way up to the last one, so plus so many other terms up to the last one is the integral from x n minus 2 to xn of f of x dx. How else can you write this in terms of summation? So this can as well be written as the sum from I is equals to 0 to n minus 2 of the integral from xi to xi plus 2 of f of x dx. That's what it means. So these are in brackets. And remember, I is an even number. From 0 you go to 2 in that order. Don't go to 1 etc. Where I is equals to 0, 2, 4, all the way up to n minus 2. So that's in terms of summation. That's what we have. Now let's focus on the integral inside the bracket. Once we have found the value, we will now sum from I0 to n minus 2. So you can say that now let's work out that integral. It is the integral from xi to xi plus 2 of f of x dx. This is approximately equal to the integral from xi to xi plus 2. Replace f of x by the interpolating polynomial of degree 2, this one here. So that would be fi plus s delta fi plus s minus 1 over 2 factorial delta squared fi. And this is with respect to x dx. So you see now we are changing to a new variable s. The transformation is this one. You let s be equal to x minus xi over h, so that when I make x the subject, I'm going to get xi plus sh. So this transformation will always transform the x values to integers. So I need to differentiate. This one, dx, ds, I mean. When I differentiate, I'm going to get this dx, ds. That should give us h. So, or dx is equals to h ds. That's very important, because we are replacing anything to do with x. We want now the new integrand to be a function of s. What about the limits of integration? Let's get the new limits of integration. So you can write your limits. So we start with when x is equals to xi. If I substitute xi, what will I get as the value of s? So that means s will be xi minus xi, which is 0. Then over h, that will give us 0. And when x is equals to xi plus 2, what will be our s? S will be, remember, if we have here xi, here we have xi plus 1, and here we have xi plus 2. And the spacing is h, equal with h. So when we put x is xi plus 2 here, we'll have xi plus 2 minus xi, and from our diagram, xi plus 2 minus xi is equals to 2h. So that is 2h over h, which is simply 2. So now the new limits are from s is equals to 0 to 2, so that our integral will now be the integral from 0 to 2 of fi s delta fi. Remember, when I write fi, it simply means it is the value of f when x is equals to xi. That's what it means. Then plus 1 over 2 into s squared minus s delta squared fi. Instead of dx, I'm going to write h ds. So there's ds here, and there's h. Because h is a constant, you can just factor out of the integral. So let me insert it here. So this h is equals to that. So you see now our new integral is in terms of s. The integrand is a function of s, and so we have the limits from s is equals to 0 to 2. Let's integrate. So of course you're going to use power rule of integration. When you integrate this, you're going to get h, then s fi plus s squared over 2 delta fi plus 1 over 2 s cubed over 3 minus s squared over 2 delta squared fi. from 0 to 2. That is from S0 to 2. S is equals to 0 to 2. Of course, you start with the upper limit. When S is 2, what are we going to get? 2Fi plus 2 delta Fi plus 1 over 2, 2 cubed over, that is 8 over 3, 2 squared over 2, that will give us 4 over 2, which is 2. Delta squared Fi. And remember, when S is 0, the result is 0, which I don't need to write. So this you can as well write as, what is 8 over 3 when you subtract 2? What are you supposed to get? So that is the question. That should be able to give you, of course, when you multiply again by 1 over 2, you should be able to get 1 over 3. So this you can as well write as H 2Fi plus 2 delta Fi plus 1 over 3 delta squared Fi. Now I need to know those the delta Fi and the delta squared Fi in terms of the functional values. So you need to recall our definition of the forward difference operator. Let me write it down. That our forward difference operator, delta, you can write a note that delta Fi, you say this is the same as Fi plus 1 minus Fi. What about delta squared Fi? This is the same as delta of another delta Fi. And we know delta Fi, so this you can write as delta of the innermost bracket is Fi plus 1 minus Fi, which you can as well write as the forward difference of Fi plus 1 minus the forward difference of Fi. And when you work it out again, forward difference of Fi plus 1 will give you Fi plus 2 minus Fi plus 1. That's the first bracket. So that's forward difference of Fi plus 1. Then minus forward difference of Fi, we said this is the same as Fi plus 1 minus Fi. And so when you simplify, you'll get Fi plus 2 minus 2 Fi plus 1 plus Fi. So I'm going to substitute them. I'm going to replace this delta Fi and also delta squared Fi with the functional values that you have found, so that this integral can now be written as now H 2Fi plus 2 Fi plus 1 minus Fi plus 1 over 3. And then we have Fi plus 2 minus 2 Fi plus 1 plus Fi. And if I factor out 1 over 3, I'm going to get H over 3 into, now here we'll have 6Fi plus 6 into fi plus 1 minus fi, then plus fi plus 2 minus 2 fi plus 1 plus fi. That's what we have. Now, let's combine the like terms. Here I can see, let me cancel. 6fi will cancel with this because this is another negative 6fi. So we only have this one. So that this can now be written as, let me pick red. So that is h over 3 at, in bracket fi. That's the only fi that we remain with, this one here. What about fi plus 1? We have 6 fi plus 1 minus 2 fi plus 1. So this and this will give us 4. So you write plus 4 fi plus 1. And then lastly plus fi plus 2. Fi plus 2. That's what you get when you simplify. So that integral is given by whatever we have found. So we can write it down here and bracket it. So this value of the integral that we have found, we are going to substitute it into that summation. In fact, we could have called this equation star, this one, so that we replace that in equation star. So we can say hence equation star becomes, remember on the left is the integral from a to b of f of x dx, which is the summation from I0 to n minus 2 of the integral that we have just evaluated. So you can just say that this, hence, equation star becomes the integral from a to b of f of x dx is now approximately equal to the summation from I is equals to 0 to n minus 2 of the answer we have found is h over 3 times fi plus 4 fi plus 1 plus fi plus 2. That's what we have found. Now, if I put I0, what am I going to get? So this is equals to, when I0, you get h over 3 f naught plus 4f1 plus f2. When I is 2, remember I is an even number, you can say I is equals to 0, 2, 4, all the way up to n minus 2. So when I is 2, I'm going to get h over 3 f2 plus 4 f3 plus f4. So you can proceed with the same, the values of I. You see, you cannot write everything. Let's say we can go to the next one, or simply the last one where we have I is equals to n minus 2. So we can say here we have so many other terms because you can't write everything. Up to when I is n minus 2, what are we going to get? H over 3 f n minus 2 plus 4 f n minus 1 plus f n. And so you can simplify this further. This you can as well write as, you see h over 3 is common, so I can factor out h over 3, so that inside the bracket we have f naught plus 4f1 plus F2. Again, plus another F2 plus 4F3 plus F4 plus there are so many up to the last one is Fn minus 1, minus 2 I mean. This is minus 2 plus 4 Fn minus 1. Then the last one is Fn. And so you can see some of them have the coefficient of 4 and some of them have been repeated twice. So we can continue to simplify this further. H over 3, F naught. Do we have any other F naught? I can't see it. So that's F naught. Let's take those with the coefficient of those that have been repeated twice. I can see F2 has been repeated twice. Which other one again? Even F4, inside here there's F4 has been repeated twice, or even Fn minus 2. So we are going to write here plus 2 F2 plus F4 plus so many of them up to Fn minus 2. Those are the ones that have been repeated twice. Then those with the coefficient of 4. That means they have been repeated 4 times. It is 4F1 there, 4F3, even here. So you can write F1 plus F3 plus, there are so many, up to Fn minus 1. Then lastly, we have Fn. So that is this. Now, what you have found here is what we are calling the Simpson's a third rule. So let me write it down and then bracket it and explain why. Of course, I'm going to give you the rule in words. So let me write the same rule down and then we talk about it. So if you look at this rule, you realize that the end ordinates F naught and Fn, they just appear in one. So it's, yeah, we can talk about this rule in words. In words, this is the same as the integral from a to b of f of x dx is approximately equal to h over 3. Then here we'll have the sum of end ordinates, sum of end ordinates. That is f naught and fn. Then now we have plus 2 twice the sum of middle ordinates whose subscripts are divisible by 2, whose subscripts are divisible by 2. You can see it, this one. Then lastly, plus 4, the sum of middle ordinates whose subscripts are odd. So that is the rule in ones. Simpson's third rule in words. Now, the restriction in using the Simpsons third rule is that n must be an even number. So caution, or simply the restriction in using the rule, so you can just write a note, NB, that the requirement is that n must be an even number. N must be an even number. Even number. I've written that in capital just for you to take a question that when you're using Simpson's 1/3 rule or a third rule, first of all, check to ensure that the spacing or the n is an even number. If that is not the case, then you cannot use this rule. It can never work. And an even number is a number that is divisible by 2. Now, because we are saying this rule is just an approximate, it will give you an approximate solution of the given integral. It means there is what we call the truncation error that you incur by using the Simpson's third rule. So let's see the accuracy of this method, or what we are calling the truncation error bound. So I'm going to write it down here. So we all know that when you talk of error, it is always the exact value minus the approximate value. Now, how do you get the exact value? And how do we get the approximate value? So let me write here that error is equals to exact value minus the approximate value. So let me show you how to get the exact value of that integral. So we start with exact value. I'll write in another color, exact value. Our task was the integral from a to b of f of x dx, evaluating that integral. So what you need to do is to expand f of x in Taylor series. Expand f of x in Taylor series about xi. Remember the Taylor series expansion of any function about xi, f of x is equals to the sum from n is equals to 0 to infinity of the nth derivative of that function at xi over n factorial, then x minus xi raised to n. That's the Taylor series expansion of any function about at the point x is equals to xi. So when you open up that summation, this is what you need to get. It will be equal to the integral from a to b. Now, instead of a to b, let's talk of the integral from xi to xi plus 2. And then we now sum it, because once you know that, then you can be able to get the whole integral from the interval a to b. So first of all, let's start with from xi to xi plus 2. So this will be from xi to xi plus 2. That expansion will give us f f of xi, which is fi, plus fi prime times x minus xi plus fi double prime over 2 factorial times x minus xi squared so you can go up to degree 4. So continue and write plus fi third prime over 3 factorial x minus xi cubed plus fi, the fourth derivative, over 4 factorial x minus xi, and that's raised to 4. Remember, we are going all the way up to infinity, so we expect so many other terms here up to infinity. That's what we need to integrate with respect to x. Now, how do you evaluate this integral? It is not easy to evaluate the way it is. We need to use u substitution or even the t substitution. Let t be equal to x minus xi. So let t be equal to x minus xi. So that means the derivative. This simply means that dt dx will be equal to 1, or simply dx is equals to dt. When you differentiate, what about the limits? When x is xi, what will be t? When x is equals to xi, there should be equal sign. When x is equals to xi, you'll find that our t will be 0. Our t will be 0. What about when x is equals to xi plus 2? What will you get? Our t will be equal to 2. So when you substitute here now, our integral will now be the integral from t is equals to 0 to 2 of fi plus fi prime times t plus fi double prime over 2 factorial times t squared plus fi third prime over 3 factorial times t cubed plus fi, the fourth derivative, over 4 factorial times t raised to 4 plus so many other terms up to infinity. Now dx now becomes dt. So it is now easy to integrate this one. Use power rule of integration. So when you use power rule, this is what you're going to get. So that's what you get, but there's something I need to take note, I need us to take note of. Remember, when you take xi plus 2 minus xi, you get 2h, not 2. There's a h here. There's h, 2h. So take note of that. It should be 2h, not 2. Because we said the interval between, let me just explain here why it is h. If I have here xi, I have here x I plus 1 Then we have xi plus 2. So you know the spacing is h. So, and we said t is equals to x minus xi. So when x is xi plus 2, so when you take xi plus 2 minus xi, you get 2h, not 2. Similarly, when you take xi minus xi, it is just 0. So the correction was the h that was missing. So now let's plug in the limits of integration. When t is 2h, what are we going to get? And when t is 0, of course, everything will be 0. So let's just work with 2h. So when you plug in the limits of integration, where there is t, you put 2h. So we'll have 2h times fi, then plus 2h squared, that is 4h squared over 2. That will simply be 2h squared fi prime. So that would be 8h cubed over 3. So 8 over 3, 3 times 2 factorial. So that's 8 over 6. 8 over 6 is the same as 4 over 3. So I'll rub 8 so that this becomes now 4 over 3. H cubed fi prime. Of course, double prime. 2h raised to 4, that is 2 raised to 4 is 16. Then times h raised to 4. 16 over 4, that is 4. Then divide by 3 factorial. So that's 4 over 6, which is 2 over 3. 2 over 3, h raised to 4. Then the third derivative at xi. And finally, 2 raised to 5, that is 32. 32 divided by 5, then times 4 factorial. What will you get? So 4 factorial, remember, is 4 times 6, which is 24. So 24 times 5, that is 120. So 32 over 120. When you simplify, you get 4 over 15. That will give us 4 over 15. H raised to 5. Fi, the fourth derivative, plus so many other terms. So that's what we get. That is the exact solution of that integral. What about the approximate solution? Let me take you back to the approximate solution because we already found it. We can write here approximate solution. How did we approximate the integral from xi to xi plus 2 of f of x dx? It was approximately equal to, I'll take you up so that you see where we got it. You don't need to repeat. In fact, we even bracketed it. It is this one here, the one that I've ticked. We said it's h over 3 times fi plus 4fi plus 1 plus fi plus 2. So I'll take you down and write it there, what we got. So what you do next is now, you see we have fi plus 1, fi plus 2, and look at our exact solution. Everything was fi. So what I'm going to do is to express fi plus 1 and fi plus 2 in terms of fi. So I'm going to explain here. that we express this in terms of xi, express in terms of fi. And how do we do that? You need to expand those two in Taylor series, expand in Taylor series. Taylor series about xi. Expand in Taylor series about xi. So we are going to expand each of them. Let's see how to expand fi plus 1. So the expansion for fi plus 1 is this one. Remember, when we write fi plus 1 is the same as f of xi plus 1. And what is xi plus 1? Xi plus 1 is the same as xi plus h. You can see it here that when I take xi and you add it to h, you get to xi plus 1. So xi plus 1 is xi plus h. When you want xi plus 2, it will be xi plus 2h. So I can just write here that xi plus 1 is equals to xi plus h and xi plus 2 is the same as xi plus 2h. It is clear from there. So now let's expand, and you know the Taylor series expansion for f of x in general. So where there is f of x in this expansion, I'm going to put xi plus h. So you see here, when I replace x by xi plus h, what are we going to get? Where there is x, I'm going to replace by xi plus h. So you see, even the xi will cancel with this, so we'll just have h raised to n. So that's the series. So let me write it down here. Now this expansion is the same as fi plus fi prime times h plus fi double prime over 2 factorial times h squared plus fi third prime over 3 factorial h cubed plus fi the fourth derivative over 4 factorial h raised to 4. Of course, there are so many other terms because we are going all the way up to infinity. So that is fi plus 1. Also, let's expand fi plus 2. So similarly, the expansion for fi plus 2. Remember, I told you fi plus 2 is the same as writing f of xi plus 2. And so xi plus 2 is the same as xi plus h. So here we'll have f of xi, I said plus 2h. Again, when you expand this, we will have fi plus fi prime Now 2h squared. No, it's just 2h, not 2h squared. What I'm doing is this. Look at our series, Taylor series. Now instead of replacing x by xi plus h, now this one will be 2h. When there is h here, put 2h. Even here, that is now 2h. And here it is 2h. So you see, we'll be having 2h raised to n because the x's will cancel. So every time you are raising, it is 2h raised to n, where n ranges from 0 all the way up to infinity. So that here we'll have 2h, and then the other one is now fi double prime over 2 factorial 2h squared, that is 4h squared, followed by fi third prime over 3 factorial. Now 2h cubed, 2 cubed, that is 8, so that will be 8h cubed. And then lastly, we can go up to order 4. The fourth derivative over 4 factorial, 2h raised to 4, that would be 16h raised to 4. Remember, there are so many other terms. So, having known those ones, let's now substitute them back here into this approximation. So I'll need 4 times fi plus 1, then you add it to fi plus 2. So you can just write that, therefore, I'm replacing everything. The integral from xi to xi plus 2, xi plus 2 of f of x dx is approximately equal to, so that was h over 3 times fi. Now 4 times the whole of this, what will we get? And then add to this other one. So when I multiply this by 4, let's see what you're going to get. So it will be plus 4 fi because I can put this in bracket, plus h fi prime plus h squared over 2 fi double prime the other one is h cubed over 6, h cubed over 6 fi third prime. And lastly, we have h raised to 4 over 24. 4 factorial is the same as 24. Fi, the fourth derivative. Remember, there are so many other terms. Then add it to this other one, fi plus 2. So let me write it here. So when you simplify this, the whole of this, whatever we have in the bracket, you need to get 2h fi plus 2h squared fi prime plus 4h cubed over 3 fi double prime plus 2h raised to 4 over 3 fi third prime plus 5h raised to 5 over 18 fi fourth derivative plus so many other terms. So this is the approximate solution. Now, let us subtract now because now we need the error. the error is the approximate solution, or simply the exact minus the approximate, what we wrote here. So we are going to do the subtraction. Substitute there. Just to take you back to the exact solution, it was this. Let's call it equation A. That was exact. And now our approximate for the same integral is this one. Let's call it equation B. So error is equation A minus equation B. So you can write here that the error, of course the error we did not buy is subscript I. Let me just write error, which is denoted by E subscript I, is equals to equation A minus equation B. So do the same subtraction. Look at the coefficients of Fi. In equation A, what is it? It is 2h. And in equation B, it is again 2h. So those will cancel. What about Fi prime? Let's see, in equation A, it is 2h squared Fi prime. And equation B, it is 2h squared Fi prime. Again, those will cancel. So another one, Fi double prime, that's 4 over 3h cubed in equation A. In equation B, again, the same value, 4 over 3h cubed. What about the third derivative? In equation A, we have 2 over 3h raised to 4. And in equation B, let's see what it is, whether it is the same coefficient. Again, it is 2 over 3h raised to 4. So all those terms will cancel except the fourth order term. So when you simplify it, now we'll have, you can just say or EI. Remember, I don't need to write everything because I know some terms will cancel, just to save on time. So that will be equal to, check the coefficient of the fourth derivative in equation A. That is 4h raised to 5 over 15. So that is 4h raised to 5 over 15 minus the other one is 5h raised to 5 h raised to 5 over 18. So this is the coefficient of the fourth derivative of Fi. And so there are I order terms, so there are so many other terms all the way up to infinity. So when you work out 4 over 15 minus 5 over 18, you can press that in your calculator so that you see what you get. That, of course, will give you negative 1 over 90. So this is the same as negative h raised to 5 over 90. That's what you need to get. Then times Fi, the fourth derivative, plus so many other terms. But you see, when we talk of the error, we are always interested in the absolute error. First of all, before we get the absolute error, let's truncate this series, because see, this series goes up to infinity. So truncate it up to the fourth order term. So truncate up to the fourth order term to get we can say truncate this series. Up to the fourth order term to get so I'm going to ignore the higher order terms. So you can say error E subscript I is approximately equal to negative h raised to 5 over 19 over 90 times fi fourth derivative. So the absolute error, we now take absolute on both sides because we are interested in knowing the magnitude of that error. Because you see, error can be positive or negative, but when you talk of error, it's better to talk of error when it is absolute. So absolute of this one will give you h raised to, remember h is positive, over 90 times the absolute of the fourth derivative of that function at x is equals to xi. So that's the absolute error. Now, you know that h is b minus a over n. H is b minus a over n. So you can write put h is equals to b minus a over n. So what are we going to get? It will now be equal to, now I'm going to split the h so that h raised to 5 is the same as h raised to 4 times another h. So we'll now have b minus a over 90 instead of a 90, let me just write it this way. I'll have it as h raised to 4 over 90 times the other h, which I'll now write as b minus a over n, then times the absolute value of that fourth derivative of fi. That's what we have. Now, the approximate bound for the truncation error in estimating the integral from a to b of f of x dx, that is using Simpson's third rule, with n over 2 subdivisions of width 2h is given as, so of course you see this is e substitute, right? So we add all of them so that you say that therefore the total error is simply the sum of the errors from I is equals to 0, 2, 4, etc. So right here, the total absolute error is given by I'll write it down there. So our total error, which we denote by E, of course, total absolute error. Remember we said I ranges from 0 all the way up to n minus 2. So just when I is 0 plus when I is 2, when I is 4, etc. up to when I is n minus 2, the sum of all those absolute errors. Now, we said E substitute I is the same as h raised to 4 over 90 times b minus a over n times the absolute of fi at the fourth derivative. So you just substitute when I is equals to 0, what do we get? When I is equals to 2, what do we get? When I is equals to 4, etc. up to when I is equals to n minus 2. We're just summing them. Now look at this bracket. This one here. This is the sum of all those fourth order derivatives for I0, 2, 4, all the way up to n minus 2. If I pick the maximum between the interval a to b of the fourth derivative of the function, it will be bigger than every other value that you can think of in that bracket. And how many terms are there? There are just n over 2 terms. Because you see, from 0 we go to f2. Then we go to f4. We have jumped another f1. We have jumped f3. We have jumped f5, etc. So we have just picked n over 2 of those fourth order derivatives. That's why I have here n over 2. Not n, because you see we have jumped f1, f3, etc. So we picked all those with the subscript f1. So when you simplify this one, n will cancel with this n, and 90 will multiply 2 to give us 180, so that this will now give us b minus a over 180, then times h raised to 4. So let me write b minus a over 180 times h raised to 4 times the maximum, that should be maximum. So write maximum between a less or equal to x less or equal to b of the absolute of the fourth order derivative of that function f of x. That's how to get the truncation error bar. So let me write it down here and then bracket it. So we have derived the formula for the truncation error bound when using Simpson's third rule, and also the formula for the Simpson's third rule. Now we can go back and answer the questions. Let me take you back to the questions. So we can answer now question number 1. Remember, we are done with the discussion of the Simpson's third rule. Now we need to work out question number 1. In number 1, we need to estimate the integral from 1 to 1.3 of root x dx using Simpson's third rule. We are given h to be 0.05, and once you have found the value of that integral, of course the approximate value, you need to also find a bound for the truncation error. So we do number 1, we have done discussion. So let me take you down to where we need to solve problem number 1. So first of all, we need to know whether n is even or odd, because you must be certain that n is even for you to be able to use the Simpson's third rule. So n is always b minus a over h, b minus a over h. Of course, our a is equals to 1, so this is our a. This other one is our b, which is equals to 1.3. So we can substitute, that is 1.3 minus 1 over 0.05. Let me write it here, 1.3, that should be 3. So 1.3 minus 1, the whole of this you divide by 0.05. So you can press that in your calculator and tell us what you're getting. Let me also press it. And remember, if you get an even number, then it means you are free to use this formula. So when you press it, you're going to get 6, that your n is 6. And 6 is an even number, so we can comment on this. This is an even number. Even number. So we are now free to use the Simpson's third rule. Now our f of x is a root of x. So let me just circle this and say this is our f of x, the integrand. So what you need to do is to come up with a table of x versus f of x, x versus f of x, f of x. Come up with that table. our starting value of x is 1, and the step size is 0.05. So let me draw it properly. So we'll have here, you start from 1, get the value of f of x, go to 1.05, get the corresponding value, continue adding 0.05, so that will give us 1.1. Get the corresponding functional value, continue adding 0.05, so that will be 1.15. Another 1.05, that is 1.2. Continue, we get 1.25. And finally, 1.3. 1.3. So that's what we have. So when you put 1, what is the square root of 1? The answer is 1. Again, work out the square root of 1.05. So do the same to complete the remaining values of f of x. So these are the values of f of x. So I'm interested in knowing what is f0, f1, etc. So let me assign them. This is f0, f1 in that order, f2, f3, of course, the rest, the other one is f4, then f5, f6. So we go all the way up to f6. Now, having known this function of values, or the tabular values, now use the Simpson's third rule. So our rule now states that the integral now from 1 to 1.3 of root x dx this is the same as, remember the rule? In words, it was h over 3 times the sum of the end ordinates. So I'll have here f0 and fn at the end there. Then there was 2 times those subscript divisible by 2. That is from f2. I can see f2. Another one divisible by 2 is f4. The middle subscripts which are divisible, the middle function of values whose subscripts are divisible by 2. So I can tick here, it is only this and this. Of course, the end ordinates are f0 and f6. I'll write f6 to the end, towards the end there. Then now we remain with f1, f3, and f5. So those ones you multiply by 4. So this plus 4 times f1 plus f3 plus f5. Subscript not divisible by 2. Remember there was f6 which I didn't write, so it was sum of the end ordinates. Another end ordinate is f6, so I write it here. And that's our Simpson's third rule. You know h, and you know this f all the way from 0 to 6. And so you don't even need to write those same values. You can read them from the table and just press everything in your calculator. What do you get when you press in your calculator? Give answer correct to 6 dp. So when I press in my calculator, I am getting 0.321486 as our approximate solution. So let me write it here, 0.321486. So let's get the error bound, truncation error bound. You have the formula. But again, you can also get the exact value of this integral so that you know the exact error that you incur. But in a case where you are not able to get the exact value, the truncation error bound will always give you the range of the possible error that you can incur. So for the truncation error bound, we are going to use this formula that the absolute error should be less or equal to b minus a over 180 h raised to 4 times the maximum between a and b of that fourth derivative of the function. So we are going to differentiate the function all the way up to the fourth derivative. So you can write this. So this is, I've replaced a and b because our b is 1.3 and our a is 1. I've also replaced x. Now I need to know what is the value of this maximum. The maximum value between x is equals to 1 and x is equals to 1.3 of the fourth derivative of that function in absolute. So our function is root x. Let's get the derivatives all the way up to the fourth derivative. So I'm going to work it down here. So when you differentiate, we get our fourth derivative to be negative 15 over 16 times x raised to negative 7 over 2. Now I want to know when x is 1, what will be the fourth derivative in absolute? And when x is 1.3, what will be that fourth derivative in absolute? So you can press substitute x is 1, check what you get in absolute value. Also replace when x is 1.3, check what you get in absolute value. So these are the values. When x is 1, that absolute of the fourth derivative at x is equals to 1, we get 0.9375. And when x is 1.3, our result is 0.3743. So which is the maximum between the two? It is when x is equals to 1. So this is the maximum. So where we have the maximum in that interval, the value here will be 0.9375. So right here 0.9375. So now press everything in your calculator so that you know the truncation error bound. When you press in the calculator, what do we get? The result here will give us, let me also press so that you see what you get. When I press, I'm going to get, let me check, 0.00000001. So how many zeros? 1, 2, 3, 4, 5, 6, 7. 7 zeros and then 1. So that's correct with decimal places. Then give us 1 times 10 raised to negative 8. 10 raised to negative 8. 10 raised to negative. That's very, very small. The error is very, very small. So what is the interpretation of this? It means that our error ranges between negative 10 raised to negative 8 less or equal to the error, then less or equal to positive 10 raised to negative 8. Positive 10 raised to negative 8. That's very, very small. And so this is the error bound. When you talk of the bound, it gives you the range of the error. Of course, anything within this range is the error in that particular calculation, or simply the approximation when using Simpson's third rule for this particular problem. Let's now answer number 2. We have answered number 1. Number 2, let me take you up there to number 2 so that we see what it is. So in number 2, we need to find the number of subdivisions. Of course, subdivisions here means the value of n. We need to find the value of n. N there stands for the subdivisions. When you use Simpson's third rule for the estimation of the integral from 0 to 1 of exponential negative x dx, that is correct to 4 decimal places. So let's see how to work it out. I'll take you down. So in this integral, our a is 0. So this is our a. Our b is 1. And our f of x is exponential negative x. So this will be our f of x. Now, let me explain what we mean by an accuracy of 4 decimal places. What it means is that our absolute error, this means that our absolute error, which is denoted by the absolute of e, should be less or equal to 1/2 times 10 raised to negative 4. That's what you mean by rounding off to 4 decimal places. When you round off, you make an error of this magnitude. 1/2 times 10 raised to negative 4. And we also know how to find the truncation error bound, the absolute error, of course. So instead of this, instead of 1/2 times 10 raised to negative 4 is the same as b minus a over 180, then times h raised to 4 times the maximum between a and b of the absolute value of the fourth derivative of that function. So I'm going to replace it. So you can just say that so let me just write what I've talked about here. So our task is to find h, and then once you know h, you can be able to find n. Remember, n is equals to b minus a over h. So once you know h, you can be able to find n. Now, let's first of all find this maximum between a and b. So I'll need to differentiate our f of x 4 times, and then check the value of the fourth derivative when x is a and also when x is b. So our f of x, we've said, is exponential negative x. So let me write it here, that f of x is equals to exponential negative x. So I want to find the first derivative, the second derivative, the third derivative, and lastly the fourth derivative, which I know how I believe you know how to work out the derivative of an exponential function. So when you do it, this is what you need to get. So the fourth derivative of f of x will give us exponential negative x, the same function. Let's see. When x is equals to a, our a is 0, what will be the result? That will be exponential negative 0, which is anything less to 0 is 1, so that will give us 1. And when x is equals to b, which is 1, when I put 1, I get exponential negative 1. That's 1 over exponential function. That would be 1 point something. So let me just write those ones down here so that we do the comparison. So when you look at these two values, you realize that 1 is the maximum. 1 is greater than 0.36. So I'll just comment here and write that this is the maximum value. So in place of maximum, all that maximum between a and b, the value there is 1. So instead of all this will evaluate to 1. Let me comment. Instead of this one, our value here is 1. So now make h the subject. Of course, you know that b is 1 and a is equals to 0. So that is 1 minus 0, which is 1. So 1 over 180 times h raised to 4 is equals to 1/2 times 10 raised to negative 4. So from here, we can be able to get h. H is equals to, so you can write that down and then press in your calculator. So when you work it out, I'm getting 0.308 for the 0.07028 can round up to 3dp. Then now we can be able to find n using the formula that n is b minus a over h. So right here that n is equals to b minus a over h. You know everything, you can substitute. There's no need of writing them again because I know b is 1, a is 0, h is 0.308. When you work out this, you need to get your n is equals to 4, approximately equal to 4 subdivisions. So n is equals to 4. So, and you see 4 is an even number. So that means what we have done is very, very correct. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you'll find me right there. Also, don't forget to comment, like, and share this video. When you meet next time, we look at more problems involving numerical integration. Bye-bye.